evening for Prof.Ben in Canada. Welcome again to the last session of our short course about predictive analytics and big data. And today will be the last session with Prof.Ben Feng, and Prof.Ben Feng already here with us at the moment. For your information again, I will reiterate that we are encouraging you to participate the whole session and with minimum 70 minutes in the event. And also we will distribute all the certificates via your email, and please answer the email. And this is the good thing for you. We will provide you with the souvenirs of the short course from Ready Project. Please reply later on. Reply your the email with your address where the souvenir we have to send or deliver. So please reply that email. That's one thing. And also the last thing, at the end of today's session, we will also distribute the link for evaluation of the short course. We will evaluate with about the effectiveness, relevance, and as well as your next plan after the short course. And as usual, for our convenience in terms of keeping focus to the session, we still opening another platform for question and answer, slido.com. Please open your slido.com with the code tanda pagar hashtag and then SC16. That is our code for the slido.com. And I also welcome you all the participants who joining in the YouTube channel, Ready YouTube channel. Please also provide your question in the comment of the YouTube channel, or you can come to the slido.com with this code. Today, for the last session, I will welcome you, Prof.Ben, and all the session is yours at the moment. Please welcome Prof.Ben.
Thank you very much. Thanks for going through the announcement and allow me to focus on today's presentation. So welcome everyone. Welcome to the last lecture of this series. I hope everybody have had fun so far, and I certainly enjoy this series of lectures very much. And in the last lecture today, it's not from any textbook. I want to take this opportunity to present to you a real case study, or actually it's a research that I did in recent years. And I want to share my experience and my research topic and some of the methodologies with you. So there are kind of a lot of different pieces put together into one research topic, and all the pieces all tie together with what we've learned so far. In particular, I still remember in the first lecture, one of you asked a very good question, and that was, is there cases where we use both supervised learning and unsupervised learning to solve practical problems? And my response at the time was yes, a definite yes. And so today I'm going to show you a particular example, an example that I have experience with, to illustrate to you how we use both supervised learning and unsupervised learning, plus a couple of other predictive analytics skills and methodologies to solve one problem, right? And so The topic I'm presenting is efficient simulation design for risk management of large variable annuity portfolios. So if you search this in Google or Google Scholar, you will find my paper. And this is a paper that was just published in 2020. It was done with two of my master's students, Zanny Tan and Jia-Yi Zhang. Okay, so let's get started. Let me try to spend some time to go slowly on the problem context, right? In order to fully understand and appreciate the solution, we need to understand the importance of the problem first, okay? So by the name of it, it's a management problem. So many of you may not be familiar with what variable annuities are, but I will start by describing what a typical insurance is, and then make the connection between insurance and variable annuity. Okay, and my research focus and my research expertise is on simulation design. You're going to see a little bit of that today as well. But the main point that I want to illustrate lies on the supervised learning and unsupervised learning. So let me start with a typical life insurance, right? A typical life insurance is a product in the simplest form. You pay monthly premium. So every month you pay a couple of hundreds or a couple of thousands. And in exchange, when you pay enough premium, sometimes for 20 years, sometimes for 15 years, when you pay enough monthly premium, then whenever you die, sooner or later, whenever you die, this insurance contract is going to pay you a lump sum, right? It could be a couple 100,000, or it could be up to $1 million, depending on how much premium that you pay, okay? Then of course, the higher the premium that you pay, the higher the benefit that you receive upon the unfortunate event of death, okay? So starting from there, a variable annuity is kind of similar, right? You pay premium, and at the end of the day, when death happens, you receive benefit. The main difference is to how much of the benefit that you receive or your beneficiary receive if unfortunately in the event that you die, okay? In a typical fixed insurance contract, the amount that you pay and the benefit that you receive upon death, those are fixed numbers, both the premium and the benefit. Both of those numbers are fixed. Okay, that's a typical fixed annuity or fixed insurance. And a variable annuity is called variable because on one hand, the premium that you pay will still be fixed. Very likely that still be fixed, but the amount that you receive is no longer fixed. It depends on the market risk. Because behind the scene, what is actually happening is when you pay your premium to insurance companies don't take those money to themselves. They take those money as if that's an investment, and they put all your money into an investment account. And when the market performs well, then there's a good chance that the amount that you receive is higher than the pre-negotiated amount, okay? So it will look very much like you are paying the insurance company to invest on your behalf. So it might feel more like an investment account than an insurance product. But nonetheless, depending on which country that you're in Canada, certainly it's about tax. Insurance products are taxed differently than investment products. So insurance company would not want to sell you investment products because it's for some taxation issues, they don't want to do that, right? Let's put it that way. So in order to make the product actually looks like an insurance, then they will have to provide you with some kind of protection. And the protection will look like the following. You pay monthly premium to the insurance company. the company invests on your behalf, and upon death, the insurance company will pay you some amount. And this amount would be the maximum of a pre-negotiated benefit, which is usually like a couple $100,000. It's a pre-negotiated amount. And the benefit that you receive is floored. The minimum you're going to receive is that pre-negotiated amount. When the market is not performing well, when your investment account actually drops in value over the years, you are still going to get a minimum guaranteed benefit. But when the market actually performs well over the years, then the amount of benefit you receive upon death or your beneficiary receive upon your death would be higher than that minimum amount. Okay, so it's a maximum of the two. So all the variable annuities would have something called a guaranteed minimum something benefit. Okay, what I just described to you is called the guaranteed minimum death benefit because it's payable upon death, right? So GMDB stands for guaranteed minimum death benefit. So there's a minimum guarantee amount that you're going to receive, but if the market performs well over the years, you can get more than that. GMWB is called the, GMWB stands for guaranteed minimum withdrawal benefit. So what this does is it's useful for people close to retirement, but still earning income over the years and have a big lump sum saving. So what ended up happening is this group of people will likely put their savings, so pay a huge lump sum of savings to the insurance company, and the insurance company promised the policyholder that every year you're allowed to withdraw a certain amount from this contract with a minimum guarantee amount that you could withdraw. And of course, you could earn investment returns over the years if the market performs well. Okay, so hopefully you have an idea, right? So this kind of variable annuities has mortality risk because it's tied with when you are going to die or when you are going to get a long-term disability or any kind of mortality event that is typical in traditional insurance products. But at the same time, because your premiums are invested into some kind of investment account, then there is also a market risk attached to it. Okay. So in this kind of account, you have mortality risk, market risk, and then also from the insurer's perspective, from the insurance company's perspective, there's also some kind of policyholder behavior risk, because some policyholder, due to some other life event, they decided not to pay premium anymore. So there's all kind of policy behaviors involved as well. And all these risks are complicated in and of itself, but they also interact, right? When the market is not performing well, then it's more likely for the policyholder to cancel their policies. So these risks are not independent and their interactions are quite complicated. And there, you could put multiple guarantee minimum benefits into one policy. So you could have multiple riders and different riders may have customizable features. So what I'm trying to get at is this kind of policies are new, they are complicated, and there's no way to calculate their prices in closed form formula. So in order to get a sense of how much these contracts worth, the only possible way or the only feasible way is through Monte Carlo simulation. Okay, so Monte Carlo simulation can be as complicated as you want. So when closed form formulas are not available, you could always fall back on Monte Carlo simulation. But that's not the end of the story. If Monte Carlo simulation solves all the problems, I wouldn't be here talking to you about these case studies. So what's wrong with Monte Carlo simulation? It's flexible and it can simulate all kinds of complicated risk, and it's performing well. The problem is about computation. Right? It takes time to run simulation. Sometimes when the contract is complicated enough, the computational time is significant. Okay? So simulation is time consuming. Okay? For some of you in the audience, if you have run some simulation experiments in your previous lectures or classrooms, you may have simulated call prices, or you may have simulated put options and some option portfolios. But when the option features are simple, simulation doesn't take that long. But when you have options in a variable annuities, and the variable annuities could last for 20 or 30 years or however long the policyholder lives, well, the simulation can take quite long. Okay, so I talk about simulation taking a lot of time for simulating one policy. But if you think about the insurance company's standpoint, the insurance company, for the big insurance companies, they have a large number of contracts in a portfolio. So if it takes time to simulate one contract, it's going to take a long time to simulate the whole portfolio. Okay, so predictive analytics, at least in my study, is used to solve this computational problem. Okay, so we have to use simulation to estimate contract prices, and we want to know the portfolio value. But I don't have enough time, or I don't have powerful enough computer to simulate every single contract. What can I do? I will start with unsupervised learning or clustering. This is something I'm going to discuss a little bit today. So consider a portfolio with, say, 100,000 contracts, 100,000 complicated variable annuity contracts. Is it really necessary to simulate every single contract? Right? If me and my best friend have very similar characteristics, similar age, similar height, similar weight, and similar life behavior and life experiences, we both are not smokers, and we both are male, and so on and so forth. So in that case, probably it doesn't need the company, it doesn't need the insurance company to simulate for both of us. It might be good enough to just simulate for one of us and then just multiply by 2, right? Because our contract looks so similar. But how do you first identify a group of contracts with similar characteristics? That is the task of unsupervised learning. And then simulation, I'm not going to touch too much on this part. This is not the focus today, but I'm going to show you a little bit of tricks how we can make the simulation more efficient. Okay. And last but not least, supervised learning come into handy when you say out of 100,000 contracts, you simulated 1,000 of them. That means you have 1,000 data points with both X and Y. Then you could run a supervised learning model in order to learn the relationship between the contract characteristics and the contract value. And then you could use this model to predict, quote unquote, predict the value of the remaining 90,000 contracts that weren't simulated in the second step. Okay, so let me summarize what I do, right? What I'm proposing is when somebody gives me a portfolio with 100,000 contracts, I use unsupervised learning to identify groups of contracts that look similar, and I'm going to identify, say, 1,000 different groups And for each group, I only simulate for one contract for each group. And by that, I mean I'm going to simulate for 1,000 different contracts in the portfolio. And then I'm going to use supervised learning to learn from the 1,000 contract I actually simulated, and then to predict the value for the remaining 99,000. Okay, so that's the plan. Of course, each of these steps will require some thinking as well. So the three-stage simulation design is basically what I just said, with some numbers plugged in. Okay, so I'm going to estimate value of each contract by simulation, and I have way too many contracts to simulate individually. So I'm going to give names for the different steps, for the three steps. The first step is called a compressor, because I'm going to compress the entire portfolio into something called the representative contracts. How can I consider this subset of representative contracts, but still be able to learn the overall characteristic of the whole portfolio? So small n here would be much less than the entire portfolio. Okay, and then simulator, just as the name suggests, I'm just going to use Monte Carlo simulation to estimate either the contract value if I want to know the values, or I estimate the Greeks, delta, gamma, what have you, estimate the Greeks of each contract. Okay, so the simulation part, again, isn't the focus today. And the last part is called a predictor. Basically, you use a supervised learning model to learn the relationship between the contracts that has simulated contract values. Okay, and based on the relationship that's learned from the representative contracts, then I could use this model to predict the other contracts that weren't in the training process. Okay, and then these predictions will give me the value of Greeks for all the contracts in the portfolio. And when I sum them up or somehow aggregate values, I could get the portfolio value. And that's my point. So in my research, what I did was I tried to put a little bit innovation in every one of the three steps. And the results are quite encouraging. We have a method that improves both time and accuracy. I'm going to show it at the end. So let me spend some time on the clustering, because that's the main focus today. So let's pull ourselves back from my research and think about where we really are in this short course, right? So in this short course, we learn about machine learning models, which is categorized into two main parts. The first one is called supervised learning. And in supervised learning, there are two typical problems: a regression problem when the response is continuous, or a classification problem when the response is discrete. Okay, so before this series of lecture, I kind of assume everybody knows linear regression. And in the second lecture, I talked about logistic regression. In the third lecture, I kind of run through a classification problem. Okay, so today I'm going to focus on unsupervised learning, just to complete our discussion on all different types of machine learning problems. Okay? So supervised learning is saying, I don't have the labels, I only have the features. In the context of variable annuity, features means the different characteristics of a variable annuity. For example, age of the policyholder, the amount of benefits, and the gender and smoking behavior, and so on and so forth. Okay. It's unsupervised because there's no label, and in the context of variable annuity, you could think about label as the value of that contract. Okay, so there are many different unsupervised learning algorithms. Clustering is a common one, and I'm going to describe one specific clustering algorithm called the k-means clustering. So clustering is a class of different techniques to find subgroups, or we call clusters, in a given data set. Okay, so we don't know why we are doing the clustering, but maybe just by observing the data, we see there are different groups. Okay, for example, in a Visa card company, they don't know whether you're going to default or not, or they don't know whether you are a student or not, but they could just run a clustering algorithm to identify different people's purchasing behavior. For example, if you have low balance and then you keep purchasing laptops and notebooks and then stationaries like staples and so on, then very likely you are a student. If you keep purchasing high-end cars, houses, and so on, then probably you are not a student. So they could just cluster different characteristics without really knowing what's the end purpose of it. Okay. And a good clustering algorithm will have to satisfy two conditions, or at least they have two goals. A good clustering algorithm produces clusters with the following two characteristics. Within each subgroup, all the observations should have similar characteristics. And that's not the end of the story, right? That's at face value, that might be what we want, but that's not the only thing that we want. We want the clusters, we want the subgroups as separated as possible. So the features in different subgroups are very distinctive. Okay, so we want cluster algorithms to do these two, to have these two objectives. And clustering looks for homogeneous subgroups, which is just saying we want subgroups where they, within the group, they all look similar. There are two main classes, or two main types of clustering algorithms. Either k-means clustering or variations of k-means, and something else called hierarchical clustering. I'm going to focus on the first one today because that's what I use in my research. K-means saying, well, before running the k-means, I have to decide the number k, how many clusters at the end I want to have. Hierarchical clustering doesn't have that prejudice. Hierarchical clustering saying, I don't know what k is, but I'm going to give you a tree-like representative of all the clusters and to tell you, well, if you want one cluster, I can tell you what that cluster looks like. If you want two, I can also give you the two clusters according to my method. So you could kind of already tell that hierarchical clustering gives you more information, but there's no free lunch. Hierarchical clustering sometimes is more computational intensive. So let me just focus on k-mean, which is what I use in my paper. Let me describe the k-means algorithm in detail, or enough detail to understand what the algorithm is doing. So to initialize the algorithm, you first have to decide the number k, the desired number of clusters, and you somehow initialize the algorithm, right? At first, you have to decide k different cluster centers, and these are called the centroids. Okay? So a specific terminology for k-means and the variations of k-means. Step number two is quite crucial. Okay, Step number 2 has 2 sub-steps, and this is step number 2 is the main step in the whole algorithm. Okay, K-means alternates between 2 main steps. Remember, you started with initial cluster centers, K of them, right? K cluster centers. Then you would assign each observation to these centroids. And apparently, if you want to have if you want to have homogeneous observation within one cluster, then you better assign each observation to the closest one of the K centroids. Okay, so I'm highlighting the closest one because it says in different applications, you might have different distance measures. So there is a difference in how you tell whether two observations are close or different. You have to first decide on how you measure the distance. Okay, so then after the first step is done, after you assign each and every observation to the centroids, and then you update the location of the centroids. Okay, because centroids are meant to be in the center of the cluster. So whenever you update the membership or update the assignment of the observation to different centroids, you might end up centroids not in the center of all the observation that's assigned to it. So then you will need to update the centroids. So to make sure all the centroids always stay in the center of all the observations that are assigned to it. Okay, so if you understand these 2 steps, you understand K-means. You just keep looping between these 2 steps until the algorithm no longer do any updates. So the centroids are stable, the assignment of observation is stable, and when everything becomes stable and no longer updates, you terminate the algorithm. This K-means algorithm tries to minimize the total within cluster distance. Let me explain. Okay, so within each cluster, the within cluster distance is defined as the total distance between all the observation in that cluster to the centroid of that cluster. And because you have capital K different clusters, you sum up all the within cluster distance for all cluster, and that's called the total within cluster distance. And by doing so, you would find the elements within every single cluster as similar as possible. Because if it's not, then that observation would be assigned to a different cluster. And as I emphasized a minute ago, K-means clustering algorithm is very easy to implement. It just has 2 main steps. Okay, so probably after class, almost every one of you will be able to implement. So the algorithmic or the programming is not difficult. The difficult part is finding out a sensible distance measure. When you are given 2 variable annuity contracts, how do you tell if they're similar or not similar? Do you focus more on the age, or do you focus more on the smoker versus non-smoker, or do you focus more on something else? Okay, so calculating the distance between 2 variable annuity contract is the key in implementing K-means. Or to generalize that, depending on the application you're working on, if you want to use K-means, keep asking yourself whether you have the correct distance measure. Okay. So K-means is useful, but at the end of the day, it's a heuristic. So it is important for you to run K-means multiple times, and every single time you use a different initialization. Okay, so you first initialize with K cluster centers. So initially, you want to run K-means multiple times, each time with a different cluster center. So why do we need representative contract? I hope I've motivated this well enough, but let me just repeat that, okay? If a variable annuity portfolio, typically it's in the hundreds of thousands, right? For larger insurance companies, hundreds of thousands of contracts, it's basically infeasible to run Monte Carlo simulation for all contracts, okay? It's just not possible. And also, the other way of thinking about why we need representative contract is to think about sometimes when you have two contracts that are almost identical, you don't really want to simulate all the contracts because you could just simulate one and then multiply by however many similar contracts that you have. Okay, so just a hypothesis, maybe, just maybe, a small number of well-chosen contracts is sufficient to quote-unquote represent the portfolio. And that's why this small number of contracts are called the representative contracts. So we're going to use clustering to group similar contracts into clusters. And of course, we're going to use this. We're going to use k-means for this. And I'm going to use the center of each cluster to represent that cluster. So at the end of the day, the so-called small number of well-chosen contracts would be the centroids of my k-means clustering algorithm. And every member or every observation or every contract in the same cluster is similar. So one representative would be enough. So after describing this idea, let me revisit back the idea of clustering. So the distance measure, suppose I already have distance measure and contract Y for contract YI and YJ. Okay, the distance measure for variable annuity is somewhat difficult to come up with because in a variable annuity contract or any kind of insurance contract, the features are quite complicated. Okay, so it has both continuous, discrete, and discrete variables, as well as some binary variables as well. So it's not easy to come up with the distance measure, but I did anyhow. So the goal is to minimize the total within distance, total within cluster distance. XK is the cave's centroid. SK is the cave cluster. So the total within cluster distance will be summing up all the distance within the cave cluster and then summing up over all the clusters. Okay, that's our goal, and the way to achieve that is to use k-means algorithm. This is somewhat too detailed. I just want you to know that k-mean is a heuristic because there's no way, or at least computationally, there's no efficient way of finding the true solution to the problem that we defined. Okay, so k-means is an approximation or a heuristic that help us to minimize the total within cluster distance to an acceptable extent. Okay, it's not the solution to our problem, but it's one good approximate solution. So sounds all well and good so far, okay? But not really, not really. That's not the end of the story yet. Sometimes the portfolio is so big that even k-means clustering could take unacceptably long. Okay, so far the way I'm describing k-mean, none of the things so far I described is new, right? K-means has been a standard algorithm for decades. But I'm going to propose something new. I'm going to improve on the k-means clustering. Okay, so based on the observation that k-means clustering would be too slow when we run on the entire portfolio, we need to find something else, okay? So let me illustrate to you the problem, okay? I have a simple illustration. I'm going to simulate 4 random points in the unit cube in 2 dimensions and use that to just conceptually illustrate the portfolio, okay? A real portfolio will have hundreds of thousands of points. I'm using 400 here just to make sure the plot is clear enough for you to see. And suppose I want 8 clusters out of 400. So I want 8 representative contracts. And simple enough, I used Euclidean distance between points in the vector space to represent distance between any 2 points. So I'm going to propose my algorithm as well as the overall k-means, right? Suppose you have the luxury to implement k-means on the entire portfolio. That would be the benchmark. And then my proposal, my research proposal, is something called simple random sampling. Okay, let me, my proposal later is called SRS clustering, but now I'm using simple random sampling, means I just initialize k-mean without actually running it. So these two are 2 extreme benchmarks, okay? So on the left-hand side, that is my k-means clustering. I run k-means a couple of times. And different color means different clusters. I have 8 different clusters. And if you pay attention, then you might be able to see the center of the clusters. Okay, so on the right-hand side, what I call overall clustering, that would be just running k-means on the entire portfolio. I'm able to do that with 400 random points in 2-dimensional space, but there's no way to run. there's no way to run k-means on hundreds or thousands of portfolios in a VA contract, I mean, in a VA portfolio. On the right, it's kind of a giving up approach, right? If k-means is too slow, then we just don't run it. We just randomly say wherever the centroids should be, right? Simple random sampling just means I randomly picked 8 contracts, or I randomly picked 8 points in this picture. I just pick the points. I don't know whether they're centers. I'm pretending they are, and then assign all the points to the closest centroid. Okay, so these two are 2 extreme benchmarks. On the right, that's kind of the best we can do. On the left, that's the best we can do. On the right, it's kind of the worst we can do. Okay, and of course, I want to develop an algorithm that's close to the overall clustering. That's my goal. Okay, but still, we are not able to calculate. We're not able to run k-means on the entire portfolio. So what did I do? So our portfolio is to say, well, if 100,000 contracts in the portfolio is too many, how about we just randomly take 10% out of the whole portfolio? So the idea is I use a random sample to represent the portfolio first, but that sample is still somewhat too big, right? So I then cluster in one sample with all the centroids. Okay? So this is the result of my proposal. My proposal's name is called SRS.clustering because I first randomly sample from the portfolio and then I run k-means on that random sample. Okay, so I run the experiment 1,000 times and then plot the histogram of the total within cluster distance. The simple random centroids, so if I just initialize but don't run the k-mean clustering, I get this worst benchmark, the blue histogram. Subset clustering is a method proposed by some other researchers that was the cutting edge at the time. And my proposal is called SRS clustering. And from these two plots, we can see my method is quite close to the overall clustering, which is the best benchmark that we have. Okay? But because I only randomly sample 10%, my k-means clustering runs much, much faster than the overall clustering. So for variable annuities, you don't have to pay too much attention on this. These are how I specify the VA portfolio. My VA portfolio consists of two types of contracts. The first type of contract has the GMDB, the death benefit only. The other type of contract has two types mixing together. Okay, and also in the pricing or in the simulation of a contract, I also have gender, age, the premium of each contract, and the withdrawal rate of the GMWB, and maturity, how long the contract still have to go. Okay, so if you don't understand this, that's fine. This is basically how you specified each variable annuity. Okay, at least in a simulation experiment like the one I'm showing. So what I'm going to do is to compare the total in-cluster distance of different methods, different proposals. I have 10,000 contracts to begin with because I want to show you examples that are kind of manageable. And out of these 10,000 contracts, I want 50 representative contracts, and I divide the entire portfolio into 10 random subsets. Okay, so for fair comparison, our method, the SRS clustering, would run k-means clustering on one of the 10 subsets. So basically, randomly sample 10% of the portfolio. So results. This is my result. Okay, so the so-called benchmark or so-called cutting edge method at the time basically doesn't work, right? It's even worse than just randomly sampling some contracts in the portfolio. My method, by first doing the random sampling, then run the subset clustering, my method gets the total within cluster distance very, very close to the overall clustering method, which is the best that we can hope for. Okay, so my method then is more representative than the other methods and very, very close to the overall clustering. And then the second part, right? You remember it's a three-step approach. The second step is a Monte Carlo simulator. And in this case, I'm not going to change how I simulate the value of the contract. But what I'm going to change is how many independent replications I'm going to run on each of the contracts. Okay, and of course, I'm going to do that. Of course, I'm going to do that with some analysis or with some smart scheme. Okay, so given a fixed simulation budget, suppose I have 1 day to run my simulation, or suppose I have only 1 hour to run my simulation. That's what I call the simulation budget. And I'm going to translate time into the total number of replications that I could run for the entire portfolio. And the question I'm trying to answer is, how many replications should I give to each of the representative contracts? A simple way, if you don't want to do any math, the simplest allocation method would be just divide the total budget equally to each of the representative contracts. Okay? That would be the simplest case. But we can actually do much, much better than that. Okay? And the intuition behind is, since for every contract, we're going to calculate the sample average as an estimate, then for contracts that are more complicated, we might want to give that contract more replications in order to accurate its price more accurately. Okay, so that's the intuition behind. Then how do we formalize this kind of intuition into mathematics? Well, we can do that. Okay, so to estimate the portfolio value, let's try to just assume that the variance for each contract is known. Well, it's not, right? But let's assume it's known, and can we derive something? If that individual contract variance is known, the portfolio variance will look like this. Okay, will look like this expression is a big summation of sigma I squared divided by Ri. Okay, if the math is too complicated, don't bother, right? Basically, this is a optimization problem trying to minimize the portfolio variance by assigning different number of replications to different contracts. Okay, so this problem is actually quite simple to solve, believe it or not. So if those standard deviations and variances are known, then the solution, the optimal solution, is saying the number of replications you should assign to each contract should be proportional to the standard deviation of that contract, which makes which makes sense, right? Because when a contract is more complicated, you want to simulate more. And the optimal variance for each contract would be proportional to its standard deviation. That's well and good in mathematics, not good in practice. In practice, these standard deviations are unknown. I mean, if you don't even know the mean of this portfolio value, how can you know the standard deviations, right? Well, but we still have to solve the problem. If we don't know the standard deviation, can we at least find some approximation to those? The answer is yes. And we have two different methods of doing that. The first one is to just assume, it's a wrong assumption, but it's a good starting point. If we assume all the contracts with $1 premium all have the same variance, then the variance of each contract would be proportional to the square of the premium. And so forget about all this math. Let me just show you two conclusions. There is an assumption. If this assumption were true, well, it's not. We're going to see in the next page. If you run equal allocation, then if you plot the premium of each contract versus the sample variance of each contract after running simulation, then you're going to see a quadratic curve. If you run my method and optimal allocation, then you're going to see a straight line in the same plot. So let's just try to plot this curve and see whether this assumption is true. And I'm telling you the answer is no, right? So you can kind of see a quadratic pink curve and a green straight line, but what's happening at the bottom? What's happening at the bottom when the variance is close to 0? Well, this is data science, right? You need to dig into the pattern in your picture. Then I did dig into the details and see what's happening in that horizontal line at the bottom. Well, as it turns out, The problem is I have two types of variable annuity contracts in my portfolio, and the variance of these two types of portfolios are vastly different. Because GMWB is highly variable compared to just GMDB. So when I add a GMWB into my contract on top of GMDB, I add a lot of variability. Okay, so the $1 assumption is a wrong assumption, and the picture tells me it's wrong, and it tells me I have to do something better. And again, this is at the core of data science. You observe a problem by plotting or somehow visualizing your data. You discover problems and start contemplating the next solution. And then what I'm going to do is to say, well, I don't really know the variances and standard deviations, but can I at least estimate it? And the answer is yes. I separate the simulation into two stages. Stage number one, I use a small portion of the simulation budget to equally allocate to all the contracts. Then based on this simple equal allocation at first, I could estimate the contract variance for each of the contracts. And then I could use those estimated variances to come up with a better allocation of the remaining simulation budget. And this is the final result, okay? So the one in blue, the number of replications in blue would show up in the same plot that we saw just now. And the total portfolio variance in this curve would be the area under each curve. Okay, and obviously from the picture on the left, we see the area under the blue curve is a lot smaller than the other two. And on the right, I also show you that my method recognizes that more complicated contracts should be assigned a larger number of replications. And it does. That shows my method is actually working pretty well. How big a deal this is, right? Why am I spending so much time on this? Well, let's see. Running on a portfolio with 100,000 contracts, and kriging is a machine learning method, and in the machine learning literature, this is also known as Gaussian process regression. Okay? We don't have time to go into that, but you could think about that as some kind of supervised learning algorithm. And I use some simulation budget, 1,000 for each representative contract. And the baseline is subset clustering plus equal allocation. That was the best method at the time before my research. And clus.alloc is my method using my clustering method plus my simulation design. The performance measure is to see the normalized absolute error, because at the end of the day, I want to estimate the value of the whole portfolio. So I sum them up together divided by the true value of the portfolio. And I'm going to repeat the whole experiment 100 times in order to see a clear difference between my method and the baseline method at the time. And the result shows up saying, compared to a standard Monte Carlo simulation, so if you don't use any kind of smart design that I did, and if you don't use any kind of clustering method, I just need a fraction, less than 10% of the runtime to achieve the same accuracy as a standard Monte Carlo simulation. Okay, so that is a huge speed up in terms of computation. And also, compared to the so-called cutting edge method at the time, I designed the experiment so that my method will have the same runtime as that cutting edge method. And the improved accuracy my accuracy is about 200 times more accurate than the cutting edge method at the time with the same runtime. So that's a huge improvement in accuracy. And also some recent findings, right? This is still an ongoing continual research. It looks like once I have enough innovation, once I have a good compressor and simulator, which were the two main steps that I showed today. Once I have those two steps done, it seems different supervised learning method in step number 3 would kind of yield the same result or similar result in the last step. And that shows the main improvement in computation and accuracy comes from compressor, reducing a huge portfolio into the representative contracts, and the improvement in accurately estimating the portfolio, estimating the contract level value for the representative contracts. Okay, so once those two steps are done, the last step doesn't seem to have a huge effect, whether or not you're using a neural network versus using a Gaussian regression. So some supervised learning method fail to produce good predictions for individual contracts. Okay, so for example, a linear regression is clearly a terrible method, but nonetheless, when you add up 100,000 different contracts in the portfolio, when you have a terrible predictor, sometimes you overestimate a contract value, sometimes you underestimate a contract value. Just magically, when you add them all up together, the overestimation and the underestimation by and large cancels out. Okay, so that would explain why different supervised learning method give similar results. But we are unhappy with this finding because in a practical scenario for insurance company, you don't just want the portfolio value, you also want the individual contract value to be accurately estimated too. So some of the recent work that we are doing is try to find a good supervised learning method that give good prediction, not only at the portfolio level, but also give good prediction for the individual contracts. Okay, so this is pretty much all for today. And let me just summarize what I've gone through today. Okay, I have proposed an experiment design for estimating the value for large VA portfolios. And in my experiment, I achieved over 70% in improved accuracy with very little overhead, meaning the runtime is similar to our to some benchmark method that was the cutting edge 2 years ago. In some later experiment, the improvement is even bigger than 70%. A 3-stage procedure, but each of the steps could be different. For example, in this presentation, I use k-means as the compressor, but you could also use a hierarchical clustering in step number 1. The 3 stages are kind of separate components, and you could have innovations in each one of in each one of them, 2 of them, or all of them, right? So again, this is an ongoing research. And what's next? There are a lot of unanswered questions. Proofs what I'm proposing today, everything seems fine until somebody come and ask me, how do you prove your method work? So far, the answer is I can't, because I have not proved to you that this method actually work, and I have not proven to you what I mean by a good representative portfolio. Why do I just randomly sample and then run a clustering? Right? Why does it work? It seems it makes sense, but there's no proof. Maybe there are some cases this method just fails completely and miserably. I don't know. So without proof, a lot of what I'm talking about today would be just heuristics. And customized designs. In the last step, when I propose a performance measure, what I ended up estimating is the portfolio value, which is the sum of the individual contract value. So that's how I come up with the optimization problem for the second step, and that's how I solve it. But what if I'm interested in estimating something else? For example, value at risk, tail value at risk, or some other kind of estimates. Maybe I need to reformulate an optimization problem and somehow solve that problem in a new method again. And also, this problem interests me a great deal. Okay, I'm still constantly thinking about this problem. The way I design my three-step simulation procedure can make the three steps just go wild. They're kind of independent. I could use different kind of clustering method in the first step, different kind of simulation method in the second step, and all different kinds of supervised learning in the third step. Okay, so I don't like that, right? I don't like the flexibility of just letting each of these three components go in different direction independently. I want to have a design, I want to have a three-step simulation procedure such that each step can take advantage of the previous step. So there should be a synergy among all these three steps. Okay, so for example, I'm just making this up. I don't know the answer to this question yet. But for example, if you know there is a specific relationship between the sample variance and the variance of the mean estimate in each contract, can you use that fact to come up with a good supervised learning algorithm? How can you design that algorithm? And once designed, how can you make use of this known knowledge? Okay, so I really try to think about how do I make connection among the three steps rather than just letting them go in different direction without communicating with the other two steps. Last but not least, some of the audience may know my research well enough to know the name green simulation. That's just a slogan. What it really means is reducing simulation outputs. Okay, so simulation is a very common methodology in a lot of different cases, a lot of different practical applications. And people constantly run simulations. And nowadays, computers are fast, and people run simulation, get whatever result that they want, and then just discard or throw away all the simulations. To me, it seems quite wasteful nowadays because computer storage is so cheap. So I constantly think about methods how we can store or save simulation outputs. You don't know when in the future this simulation output can be useful. So instead of thinking about thinking about simulation as a one-time thing. So you run simulation and then throw away all the results. I would rather think about simulation as an investment, a recyclable resources. When you run a simulation, store the results, and then use it sometime in the future. Okay, so in these 3 steps procedure, the simulation results could be stored and could be useful for some other task as well. Okay, so with that, I close my presentation and then welcome any questions from the audience. And I just want to express my deep gratitude for the whole Ready team to make this last lecture series possible. And I also want to thank all the audiences, all the participants joining me. And I hope at some point in our life, we could cross each other again. Okay, so with that, I'm happy to address questions from the audience. Are the questions coming up?
Ya.
Okay.
Mbak Alin, bisa dimunculin? Yeah, we have several questions here for you, Prof.Ben.
Is it permissible in terms of regulatory purposes to classify the risk of PNC insured by clustering their claim sizes? Good question. Honestly, I don't know the answer to that. I don't know enough about regulation to answer that question, but from the implementation viewpoint, I don't know why they would resist this idea. Okay, I can see that this is not done now because nobody has done this before. But with a good illustration, I don't know why the regulators would reject this idea. Okay? I don't think there's any harm by doing this classification. How to decide the number of clusters? There's no mathematics to guide this, but you already know one answer to this question from last class, cross-validation. Okay, so split your data set into however many groups that you want. Use cross-validation to find out what would be a good number of cluster in your data set. And there is not even a good range of K that I could suggest you to try. So you just want to say, use cross-validation with 5 to 10 groups to find out what is the appropriate K for your application. Okay, so I guess the short answer to your question would be cross-validation. I'm sure there are more methods to answer these questions as well. Are there any metrics that represent trade-off between computational time for all data and the accuracy of representative data? Yes, definitely. In some sense, you could create any kind of metric that you want, especially in a research scenario, but I do not think there is a universally accepted metric if that's what you are looking for, right? So for example, a universally accepted accuracy measure would be the MSE, but I don't think there is a universal accepted measure for the trade-off between computation time and the accuracy. In a research, you could create your own metric. In practice, you might want to come up with a metric that your management understands. Okay. With the rapid development of computing hardware today, will this method continue to be effective? Good question. I wondered that question when I started this project too, right? And I keep talking to people in insurance company. And it was a surprise to me that yes, they are, even with the rapid development of computing hardware, even with the fast computers that we have, the portfolio, the size of the portfolio, hundreds of thousands of contracts, and the complexity of contracts nowadays still makes a standard simulation quite slow. Okay, so maybe I exaggerated a little bit saying this is impossible. Maybe it's still possible. You may be still possible to run on a somewhat big cluster of computer for, say, a week to get the accurate answer. You might still want to do that. But this method would still be effective in the sense that I could reduce the runtime by, say, 10 times or sometimes 20 times. And that is still valuable. Okay. So yes, I won't just say if something is too slow, just go buy a computer, right? That's not a very helpful recommendation, especially if you are the data scientist in a company. And every time there is a computational challenge, you say, you recommend a CEO to buy a new computer, then probably the CEO will come back to you saying, well, we solved all our data science problem. We're just going to fire you and start buying more computers, right? It doesn't work that way. You still need some innovation in the algorithm itself to improve how you simulate in practical scenarios, in practical applications. How did you decide the proportion of random sample used in SRS? Can it be under 10% and give similar results? And why did you choose k-means instead of hierarchical? Both are good questions. Let me answer that one by one. Question number one, it can definitely be less than 10%. In fact, I recollect in the latest experiment, I do a random sampling of just 1%. And yes, it gives similar results. I guess the natural research question is how small can I develop? I don't have an answer to that yet. I have not developed this method, this mathematical model yet. But yes, to your first question, it can definitely be under 10%. And why did I use k-means instead of hierarchical? The answer to this, I'm embarrassed to say this, it's mainly for convenience. K-means was a lot easier to implement than hierarchical. Okay, I have not tried hierarchical. It's actually a good idea to try out. Maybe later I will hire a master student to work on this idea. Please remind me again, in what case when the machine learning application is not appropriate? Not sure whether I had answered this question before. It sounds a completely new question to me. And I would say when data is extremely limited. Okay. One of the reasons why machine learning has become so hot nowadays is because we have the ability to collect huge amount of data. And both the quantity and the quality of data determines how effective machine learning algorithms are. Okay, so if there's an application where your data quantity is small and your data quality is questionable, then I will be very hesitant to use a machine learning method. In those cases, I will likely use parametric model, use statistical models, and have to force myself to accept some unrealistic assumption in order to proceed with the analysis. In my opinion, the flourishment or the success of machine learning algorithms in the recent decades really come from the fact that we have huge amount of high quality data. How to know which one simulation method is appropriate? I don't think there's much choice, honestly, right? The simulation method, if you're mentioning just the simulation stage of the three-step method, well, you always have to use Monte Carlo. The only thing that you could decide is how many random replications that you could use on each of the contracts. But if you are asking how to design a good three-stage method, knowing that each of the three steps could have multiple options, again, cross-validation, right? Cross-validation is, in some sense, so useful, it could address all of these. It's not a mathematical method. Like cross-validation gives you an estimate always, but the estimate is so useful that people trust that. How do you know that your Monte Carlo simulation is good or not? Good question. Maybe let me generalize your question outside of the context of this variable annuity. You always want to have a benchmark, right? Again, if you're talking about the specifics of each contract and how you simulate, you don't have a choice. Your contract features, whether it's a GMWB, whether it's a GMDB, that kind of determines a majority of your simulation method. You could design efficient methods using something called the variance reduction techniques. And once you apply variance reduction techniques, then you would just compare your new method with the standard Monte Carlo. Okay, so how do you tell whether your method is good? Well, you tell the improvement of your method by comparing it to a standard benchmark model. And fortunately, in Monte Carlo simulation, you always have a benchmark. Whether logistic regression will be relevant in this clustering process in this method. I don't really see how. Logistic regression is used to classify, not to cluster. Okay, so maybe there is, if you just want two clusters, right? You could pretend there are two classes, but no, still no. The clustering process is a unsupervised learning process, right? You only have the features, you only have the X, you don't have any labels, you don't have Ys. So no, I don't think you can even run a logistic regression at all. No, it's not applicable in the clustering process. Nonetheless, you can possibly, although I don't think that's a good idea though, you could use logistic regression as the predictor as a supervised learning method in stage number 3. But again, I don't think it's a good idea in this application. Is there software other than R that enable us to run the predictive analytics using the steps that you propose? Oh, definitely there are many of them. Okay, R is convenient in a sense a lot of people know it, and it's easy to communicate, and also the fact that it's free makes the communication easier, because you could get people started on it and say, well, it's a free software, so there's no excuse why you don't want to use it. So R is useful, but equally useful could be Python, right? Python is also one of the most popular, if not the most popular programming language in machine learning nowadays. And also, if you're in school, MATLAB would be the standard programming language for a lot of students, but that would depend on your school paying for MATLAB. And also, my wife worked in a PNC insurance company, and their company uses SAS, SAS for predictive analysis. So yeah, there are plenty of softwares. Let me just suggest a few criteria of selecting what is a good software for you. Again, these are just based on experience and rule of thumb. It's not a textbook thing, right? You want to use a software that's popular, so you could easily communicate whatever you write with your collaborators. So popularity is definitely one concern. The community means how many people are developing or helping to develop a language, right? R is an open source software, and a lot of people participate in writing R libraries. I write R libraries as well. So if you have a lot of contributors into a programming language, then this programming language will be alive for a long time. And if a lot of people contribute to this language, then more often than not, whatever you're trying to do, there might be already a package that helps you achieve that goal. Okay, so when I write in R, whenever I have something that I want to do, I will search for packages, and only I have over 90% confident that there's no one else have tried this before, then I will start writing my own. Okay, so for example, in the k-means algorithm, I initially wrote my own k-means, but later on I discovered there is a package that runs k-means and then a lot faster than my code, then I use that package. Okay, so also community support is not only from normal users, but also from big users. Python nowadays becomes so popular, especially in machine learning and neural network, because you have Google developing TensorFlow, and you have Facebook developing PyTorch. Okay, so you have these huge companies trying to help you develop packages in machine learning, and that is a huge booster in promoting these languages. Okay, so I hope some of these criteria will help you in the future in how you select a good programming language.
Yeah. Okay, that's all the questions.
Yeah.
Yeah, Bapak Ibu, this is last. I think this is the last minute to have a contact, to have a discussion with Prof.Ben. If you wish to have a direct discussion, please do. We have maybe 2 minutes left. If and also for those who already feel sufficient yourself, with the material, please fill the evaluation form. I send it to chat room. Please, you can access it. Oke. Ada lagi Ibu Bapak yang ingin bertanya ke Pak Ben?
Baik, saya Pak izin Pak Ihsan.
Oh ya, silakan Pak Eka. Please.
Baik. Terima kasih Pak Ihsan. Thank you Pak Ben. Oh, let me start my video. In a minute. Okay. Yeah. Okay. Okay. Good evening, Pak Ben. Thank you for the lecture. It's been an amazing session. 4 session.
Thank you very much.
Thank you. Thank you for having us. Pak Ihsan, you too. Thank you for having us. I have a little question. I recently joined the ITK Kalimantan Institute of Technology in Balikpapan, and you told us in one of the last slides that the problems that arise still how to quantify the representativeness. Is it correct? Okay.
Yeah, in the last in the future work, yes.
Yeah, in the future work. Do you have any idea yet on how to quantify the representativeness? Or is it what's I mean, what's in your point of view, which one will you select first, whether to develop or to develop better algorithm or proving the quantitativeness of how to select proper representative? Thank you, Prof.Ben.
Yeah. Remind me if I forget some of your questions. I'll try to answer the question that I kind of contemplating answers for. What I mean by the selecting representative contract, right? It's kind of an after fact selection of what representativeness means. Okay, so initially in the clustering step, when we try to cluster the contracts, we cluster on the X space, right? So we cluster on whether a person is male, female, and the age and the premium. So it's the front end of a variable annuity contract. On the X feature space, we do the clustering. But then I'm unhappy with that because what am I trying to really cluster is to cluster different groups of contracts with similar labels, right? Does that make sense? So at the end, I want to cluster contracts based on the Ys. But in the clustering step, I'm clustering based on the X, right? So I'm trying to find a way where I could either run some kind of cross-validation or some kind of pilot study to cluster not only on X. I still want to use X. X is still useful, but I want to somehow include Y in the clustering process. Okay? So I might have some terrible but still meaningful estimation of Y by a small number of simulation, and then I use Y in the clustering process. So then I can have a group of contracts that are not only similar in their characteristics, but also similar in value. Okay, so that's what I mean. I'm not very successful yet because somehow in my clusters, I always have some outliers. There are some contracts that looks similar with the others, but have very different contract value. And I'm still trying to understand what happened and why that is the case. Okay. I'm sure you have other questions that I forgot.
It's okay. Later. Well, I'll email you later.
Okay.
Thank you.
Yep, no problem. And by the way, if you're interested in this research, I have an R library on pricing variable annuity.
That would be great. Thank you, Prof.Ben.
Yeah, I will type in the package name in the chat. So if you're interested, you could look at it. It's called VAMC, Variable Annuity Monte Carlo.
Okay. I think that will be the last question for us because it's already quite, yeah, this is the time for us to conclude of today's session, as well as the whole series that is facilitated by Pak.Ben. And I really appreciate for your willingness and facilitation, Pak.Ben. And I think we close
My
to Pak.Ben.
pleasure. My
Uh,
pleasure.
and Ibu Bapak, thank you for your participation. I think I see you are very active in terms of your question. There are lots of number of questions in the slido.com, as well as your participation keep around 90 participants present, hadir from the beginning, from session 1 up to this session, and that's very wonderful participation. And thank you very much for you, as well as for our viewer in YouTube Ready channel. Thank you for your participation as well. And for the last session will be facilitated by Bapak Syafri Bahar. He is the Vice President of Data Science of Gojek Indonesia. And please stay in touch with us with this series of predictive analytics and big data shortcuts. And for Pak Syafri later on will be the instructor, and the topic is about the application of big data in industrial context, especially in Indonesia. I think Pak Safri will elaborate about his experience in Gojek company, because Gojek, as you know, is a that what is it, the one of the giant high tech company in Indonesia. And thank you, Pak.Ben, again. Thank you for everyone. Selamat good evening, and kita bisa berpisah di sini. We say not saying goodbye, but see you later, maybe. And thank you, Pak.Ben, Bapak Ibu sekalian. Terima kasih. Saya juga menyampaikan kepada Ibu Yvonne dan tim, ada Mbak Alin, Mbak Erni, dan tim Ready. Thank you for Ready team who facilitating organizing this short course, especially with the series facilitated by Pak.Ben. Thank you very much, and see you
My pleasure.
next Friday.
Thank you for having me.
Last session with Pak Syafri Bahar. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.